Inorganic Chemistry 1, Stereochemistry and Bonding, Unit 2, Phosphorus, Nitrogen and Sulfur-Nitrogen Compound, Content, Objective, Introduction, Phosphazene, Phosphonitrile Compounds, Cyclophosphazenes, Structure and Bonding in Phosphazenes, Structures of NpCl2,3, Structure of tetrameric phosphazenes, Uses of phosphor polyphosphazenes, 2.6 Phosphorus-Sulfur compound. Significance. Synthesis of cage phosphorus sulfides. Structure of cage phosphorus sulfides. Sulfur-Nitrogen compound. Significance. Synthesis. Structure and bonding. Summary. Terminal questions. 2.9.1 Long answer type question. 2.9.2 Short answer type question. 2.9.3 Objective type question. 2.10 Reference and step further studies. 2. Objectives. Objectives of these units are to introduce you with the synthesis structures, bonding and some application of inorganic compound of chalcogens, oxygen and sulfur with their neighboring group 15 members, nitrogen and phosphor. The chapter will deal with phosphonitrile, phosphorus-nitrogen, phosphorus-sulfur and sulfur-nitrogen compound. It will help to establish an understanding towards the structure and bonding in this compound. 2.1 Introduction. The phosphazenes, phosphoro, phosphonitriles, and sulfur nitrogen compounds are an important class of inorganic compounds which exhibit interesting structures and bondings. They may present cyclic structure motifs which may be considered as inorganic aromatic analogues. The reaction chemistry of this compound is not less interesting than those of borane. However, the revelations of exact structure for some of the nitrogen-sulfur compounds took over 100 years after their discovery. The polymer SNX was first discovered in 1910, and further investigations revealed that it comprised of only non-metallic elements and behaved as superconductor at 0.26 Kelvin. Such a discovery fueled interest in SN chemistry. Their unique structure and property continue to attract attention of several theoretical chemists who have tried to look into the aromatic character of binary sulfur-nitrogen system. The reaction between phosphorus pentachloride and ammonia was described in 1834. The major reaction product was phosphum, and a small quantity of compound containing phosphorus, nitrogen, and chlorine was also obtained. Later, the compound was designated as N3P3Cl6. This discovery led to the advent of phosphazene chemistry. They have several applications in material chemistry, biochemistry, organic synthesis, and polymer chemistry. 2.2 Phosphazene Phosphonitrile phosphor-nitrogen compound. The term phosphazene or phosphonitrile include this compound which have phosphorus and nitrogen atom joined alternatively by single or double bond. Overall, they may constitute a ring or a chain motif in which nitrogen is trivalent and phosphorus is pentavalent. The empirical formula for very first phosphazene N3P3Cl6 white crystalline product obtained by reaction of ammonia with phosphorus pentachloride was derived after some error. It was first considered to be NpCl6 but later found out to be a trimer having a cyclic structure proposed by H. N. Stokes. The trimers on heating yielded elastomers known as the inorganic rubbers. Cyclophosphazenes, the cross-linked inorganic rubbers, was formed by reaction of NpCl2n with a trace amount of H2O. Thus, if the reaction is carried out in the absolute absence of atmospheric moisture, non-cross links and soluble macromolecule of NpCl2n could be prepared. Reaction of organic nucleophile with NpCl2n can result in the replacement of chlorine atoms and hence generate stable polyorganophosphazenes. A wide range of polymer with mixed substituents having varied properties can be generated if two different nucleophiles are used on the same molecule. Polydichlorophosphazine (NPCl2N) is a key precursor in the synthesis of almost all polymeric phosphazines. Scheme 1.1. 2 moles of NH4Cl react with 2 moles of phosphor pentachloride to form NPCl2N plus 8HCl, which is phosphazine. NH4Cl ammonium chloride react with N phosphor pentachloride in presence of tetrachloroethane to form NPCl2 3 10. That means phosphazine plus 4HCl. Then 3 moles of ammonium chloride react with 3 moles of phosphor pentachloride. 12 HCl is released and form NPCl2 3, which is phosphazine. 3. Synthesis of polymeric phosphazines. First, macromolecular substitution of phosphazine. Commonly followed route of macromolecular substitution to generate polyorganophosphazines are as depicted scheme 1.2. NPCl in presence of alcohol sodium or alcohol CH2CO3 in presence of THF, we get this compound, this molecule, which is POOR double bond N. Then phosphazine react with alkyl will amine in presence of nitrogen triethyl, in presence of THF, we get PNHR NHR double bond N. Then NPCl in presence of amine in presence of nitrogen diethyl THF, we get P double bond N Cl NHR. Amine react with nitrogen triethyl in presence of THF, we get N double bond P NHR NHR1 NHR2. Synthesis of polyorganophosphazines. Third ring opening. Polymerization of NPCl2 3. Phosphazine in presence of catalyst NPNCl2 3, we get this compound. This is synthesis of cyclophosphazine by ring opening reactions. With the help of ring opening reactions, we get cyclic opening reactions. Fifth, synthesis of polyalkyl aryl phosphazines. Polyalkyl aryl phosphazines NPR2N are those molecules which have organic substituent directly attached to PCl bonds, phosphide or cationic initiators. This is a synthesis of polyalkyl aryl phosphazines. Synthesis of block copolymer. Macromolecular substitution of phosphazines give random copolymer due to non-specific nucleophilic substitution of chlorine atom on the phosphazine backbone. The block copolymer have wider application and considerable attention is given to their synthesis. Synthesis of phosphazine block copolymer. Polyphosphazine, cyclotetraphosphazine, cyclotriphosphazines. Now, structure and bonding in phosphazine. Polyphosphazine, cyclotetraphosphazine, cyclotriphosphazine. Structure and bonding in phosphazines. The phosphor-nitrogen bonds are short in phosphazines, 1.58 Armstrong, as compared to those in valence saturated phosphazines, 1.77 Armstrongs. This short bond length and absence of any significant alternation in bond length in cyclophosphazene and to a lesser extent in polyphosphazene indicates that these bonds are of multiple bond character. Initially, they were gave the island models according to which a delocalization occurs through d pi p plus p pi n, 3d of n and p of n, overlap resulting in an island of electron density spread over p and p units, with nodes over p center. But now it is accepted that valency orbitals do not play a significant role in bonding of the main group elements. Despite several other works and theories, negative hyperconjugation or group theory analysis on the structure and bonding in hypervalent compound, the island model is still dominant the phosphazine literature. Structure of NpCl23. It has a planar six-membered ring. The bond angle are consistent with sp2 hybridization 118 degree for P and P of nitrogen and sp3 hybridization phosphorus 108 degree for Cl-PCl angle. See figure 2.2 below, in which all bond lengths are reported in Armstrong units. Two of the sp2 hybrid orbital of nitrogen lone pair of electrons. Thus, the remaining one electron is left in the unhybridized p-z orbital. Structural details of NpCl23. In case of phosphorus, four sp3 hybridized orbitals accommodate four electrons and are used in sigma bonding. The remaining one-fifth electron occupy a vacant orbital. The resonance structure, similar to benzene, can also be drawn for NpCl23. However, the nature of bonding here does not follow the same. The resonance delocalization and aromaticity in this inorganic cyclic molecule has been a matter of debate since long. Despite the presence of delocalization in some phosphazine, not all molecules maintain planarity of ring. This factor does not make them unstable. The ultraviolet spectra of phosphazine does not show structure features similar to those of aromatic compound, organic compound, and so it is very difficult to reduce the unsaturated bonds. Furthermore, unlike benzene, the pi bond in cyclophosphazine have contribution from both p and d orbitals. Several theories have been suggested for the d-pi p-pi bonding. Some of them are discussed below. Craig's and Paddock's models. The overall between DXZ geared orbital of phosphorus with pz ungeared orbital of nitrogen result in a node due to mismatch in the orbital symmetry and sign of the wave function. DYZ orbital, which is perpendicular to the DXZ orbital, can overlap with PZ orbital of nitrogen without any nodal surface. Apart from this, there may be pi bonding between the non-bonding sp2 hybrid orbital of nitrogen, DXY or DX2Y2 orbital of phosphorus. Craig's and Padlock's model of NpCl23 structure phosphazine. Three, they were an co-worker model. As mentioned earlier, they proposed the island model. It suggested that dxz and dyz orbiter hybridized to give two hybridized orbitals which are oriented towards the adjacent nitrogen atom. This given three center bonds Np about each nitrogen atoms having the localization of electron density over them. Nodes are present over each phosphorus atom because two hybrid orbitals are orthogonal to each other. They were model of phosphazine structures. Structure of tetrameric phosphazenes. Tetrameric phosphazines have a more flexible structure than their trimeric analogues. They may have planar structure or tubboat, share, crown, and saddle conformations. The presence of a definite structure is not very obvious. Intramolecular forces play a major role in any structure. The structure of NPF24 is planar and NPCl24 is known to exist in two forms. The most stable is the chair form, also called as T form. The other form has tub conformations. The non-planar structure do not prevalent extensive delocalization in the ring. Organic analog of tetrameric phosphazine is the cyclooctatetraene. It is a non-aromatic compound because of lack of planarity, and secondly, it does not obey the Huckel's rule of 4n plus 2 pi electron. Huckel's rule was formulated on p pi bonding and bond 12 for organic compound having n equal to 1 to n equal to 4. Now these inorganic compounds do not hold organic rules for hermeticity. Here the d orbiter involved which overrule the Huckel's rules. The diffuse nature of the orbiter is suitable for bonding in nonpolar system providing greater flexibility to the ring. Tub conformations, chair conformations, conformation of tetrameric phosphazene, use of phosphazene. Small change in the substituent attached can lead to significant change in the polymer property. Phosphazenes have a wide range of application, such as high performance elastomer due to chain flexibility and high thermal stability. They are used as flame retardant due to their side chain functionality and limiting oxygen indices. Nowadays, they are being explored for such far-reaching applications as vaccine delivery, fuel cell member, matrices for tissue engineering, drugs, and gene delivery. Hexachlorotriphosphazine (HCCP), a significant amount of work has been done in preparation of novel characters those having high molecular weight by using HCCP NPCl23 by coupling the ring with multifunctional nucleophile. The polar linkage in HCCP can be used to prepare cyclolinear, cyclometrics, or dendritic structure. In the synthesis of cyclolinear structure, only two reactive sites are used out of the six available in cyclic NPCl23 units. Reaction of more than two sites leads to cross-link or cyclometrics material. So this is phosphazine react with urea to form this cyclometrics phosphazine in presence of base. Phosphorus-Sulfur compound significance. There is much attention directed towards the synthesis of multidental ligands having different donor atoms and the concept of hemiliability, the presence of one strong donor strongly bonding and other weak donor weakly bonding atom in a molecule find applications in protecting an active sites at the metal center. These molecules serve as interesting ligand system due to their donor property, which may be altered through chelation. The chelar complex are quite stable, and so the reactivity of a metal's center for a particular reaction. Example: oxidative addition can be studied without competing ligand substitution reaction. The phosphorus-sulfur compound are less stable than their oxy analogues and have lower melting point. They are used as insecticide, lubricating, oil additive, flotations, and vulcanization accelerators. Synthesis. Oxygen atom from phosphorus oxide can be partially or wholly substituted with sulfur atom to give thiophosphorus compound. This may be sulfur as a bridged atom or at a terminal position. P4S10 and P4S9 are isoelectronics and isostructure with phosphorus oxide. P4S3 and P4S7 can be obtained by using the appropriate stoichiometric quantity of phosphorus sulfur. 4 moles of P4 react with 5 moles of SF to we get 4 moles of P4S10 phosphor-sulfur compound. 4 moles of P4S3 react with octasulfur slow oxidation. We get 4 moles of P4S5. This is synthesis of phosphorus sulfur compound. Synthesis of cage phosphorus sulfide ACH3 3SN2S alpha P4S3I2 alpha P4S4 react with 2 moles of CH3SNI. Then CH3SN2S react with beta P4S3I2 to form beta P4S4 plus 2 moles of CH3SNI. Synthesis of cage phosphorus sulfides. Structure of cage phosphorus sulfide. Molecular structure of some phosphorus sulfide P4S10, P4S5, P3S3, alpha and beta P4S4 along with some significant bond distance are shown in figure 2.7. These are prepared from P4 and sulfur atom which are located at H. All these are reported in Armstrong units. P4 react with 10 moles of sulfur. We get alpha, beta, polyphosphorus sulfide structures. Sulfur nitrogen compound significance. The electron-rich SNX compound can serve as donor in charge transfer complex. Unlike phosphonitrile, the cyclic SNX compounds follow Huckel's rule for aromaticity. This factor has attracted much interest to their synthesis bonding and exploration of their overall chemistry. The sulfur nitrogen compound have been explored for their bonding with transition metal and also for their magnetic and conducting property. A variety of acyclic and cyclic sulfur nitrogen compound are known S2N2, even though a strange structure is the smallest homoleptic ring known to exist. It is the most important precursor for synthesis of several polythiazide SNX. The synthesis structures bonding of some of these compounds given scheme 2.8 S2Cl2 in presence of ammonia we get S4 N4S8 ammonium chloride. 4 moles of sulfur react with 6 moles of chlorine, react with 16 moles of ammonia to get S4N4 and 12 moles of ammonium chloride. 4 moles of sulfur react with 6 moles of chlorine and 16 moles of ammonia. We get S4N4 and 12 moles of ammonium chloride. This is synthesis of sulfur nitrogen compound. Reactions of silver metal at high temperature and low pressure with S4N4 results in thermal decomposition and formation of sulfide with catalysis, which catalyzes the conversion of remaining S4N4 to the cyclic S2N2. S4N4 reacts with 8 moles of silver in presence of 1 mm mercury at 250 to 300 degrees Celsius to get 4 moles of Ag2S, 4 moles of sulfur sulfide plus 2 moles of ammonia. S4N4 we get 2 moles of S2N2. Then S2N2 dimerize rapidly into S4N4 in the presence of nucleophile. S4N4 in presence of SnCl2 we get S4N4H4. Then in presence of AsF5 we get S4N42 plus. Then at 300 degrees Celsius we get S2N2. And in presence of chlorine we get S4N4Cl2. S4N4 react with 6 moles of chlorine to give 4 moles of S3N3Cl3 and S4 and 4Cl2 react with 6 moles of trimethyl silicon NSN silicon Me3. We get S5N6 and 3 moles of Me3SiCl. Reaction of sulfur nitrogen compound. Structure bonding. Some SN compounds show planar ring structure. It has been found that they follow Huckel's rule of 4n plus 2 pi electron. If we consider that in the planar cyclic sulfur nitrogen compound, each atom contributes 1 electron to the sigma bond and 2 electrons to a lone pair. Then sulfur has 2 pi electron and nitrogen has 1 pi electron. Or we can also explain the electron distribution as follows. At each sulfur nitrogen unit, 2 electrons are allocated for sigma bonds and 2 electrons for sulfur and nitrogen atoms for non-bonding lone pair. This 1 electron at nitrogen and 2 electron at sulfur are left, which can be used in the cyclic pi system of the ring. Considering these electron distributions, we can say that S2N2 has 6 pi electron, S3N3 minus has 10 pi electron, S4N3 plus has 10 pi electron, and S5N5 plus has 14 pi electrons. However, in contrast, as a stable pi organic molecule, the sulfur nitrogen compound mentioned above have electrons in the anti-bonding pi star molecular orbital which has a weakening effect on sulfur nitrogen bond. The stability of this compound can be ascribed to the following factors. Point A. The higher electronegativity of nitrogen compared to sulfur or oxygen lower the energy of antibonding pi star orbital, thus bringing them closer to bonding region. B. The longer sulfur nitrogen bond length reduce the mutual repulsion between any other pair of electrons. This lower the energy of the pi system. First, disulfur nitride S2N2. It is cyclic square planar molecule with sulfur nitrogen bond length of 1.65 angstrom. The nitrogen sulfur nitrogen angle is 89.6 degree, while sulfur nitrogen sulfur angle is 90.4 degree. Second, trisulfur trinitride S3N3 minus. The structure of NBU4N plus S3N3 minus is well established. It has a planar six-member ring with sulfur nitrogen bond length in the range 1.58 to 1.63 angstrom. S2N2, S3N3 minus, S4N4, S3N2 plus, S4N3 plus. Structure of some monocyclic sulfur nitrogen compound bond length are reported in angstrom unit. Structure of some sulfur nitrogen compound tetrasulfur tetranitride S4N4 cradle shaped structure belonging to the point group D 2D. Structure of geometrical feature of S4N4 and S4N4F4. Then tetrasulfur trinitride FON2. It has a non-planar ring structure. Structure of geometrical feature of SON2. Summary. This chapter had discussed the important concept to understand the bonding and structure of some interesting inorganic molecule. Here we learned that this class of compound play an important role in synthesis of several useful polymeric material. The phosphor-nitrogen and sulfur-nitrogen compound have unique chemistry and bondings and are still an area of active research, where new compounds have been synthesized and their structure have been studied. The phosphor-nitrogen compound do not obey Huckel's rule for aromaticity, while even though the sulfur-nitrogen compound follow this rule, yet cannot be compared to the aromatic compound.